All right, thanks a lot for coming to our talk on Fastplotlib. I'm Kushal, and this is Caitlin. And if you want to find us on GitHub or Twitter, that's our information here. And this is the repo for Fastplotlib, which we'll be talking about. All right, so Fastplotlib is a very new library that we've been building for just about the past year. And the goal is to be able to leverage new APIs on modern GPUs in order to do fast and interactive visualization. So for example, this is kind of an example of some of the different kinds of things that you can do with Fastplotlib. But this kind of just scratches the surface, and we'll get to demos in a few minutes. So first, before we talk about Fastplotlib, let's just go back to talk about where this all comes from and why it exists. So when it comes to the newer graphics APIs, such as Vulkan, which is cross-platform, or Metal that runs on Mac, and DirectX 12, which can run on Windows, these are all new APIs that kind of are superseding OpenGL or succeed OpenGL. Because OpenGL is kind of starting to get old and can't leverage modern GPU hardware as well as these new APIs can. So there's kind of a need for having new libraries that can leverage these new APIs. So Vulkan or any of these other APIs are way too low level for scientific visualization. So there are higher level APIs that are built on top of it. One of them is WGPU, but it's still pretty low level. It would take you about 400 lines just to draw an image. And so there are higher level APIs such as pygfx, which is a very new Python rendering engine. And pygfx is a really nice rendering engine where you can define things like a render, a canvas, a scene, objects to put in the scene, a camera to view the scene, and controllers to control the camera. And pygfx has this really nice object model where you can define objects in terms of their geometry and materials. Geometries can be things like positions, meshes, or a grid, and materials define how those objects are supposed to look like. So pygfx is currently in development by Elmar and a couple of other people at Zimmer Biomet. And it has a lot of other nice features. It has a nice event system. Like I said, there are controllers and cameras, so typical things that you would have in a rendering engine. It works in both notebooks using the Jupyter Remote Frame Buffer as well as in a desktop application with the same exact code, pretty much. And we could go on for half an hour just talking about the API, but I think it's really just more powerful that we go straight to demos. All right, and so Caitlin will be going through all of our demos.
Hello. So as Kushal mentioned, I'm going to spend the remainder of our talk walking through some demos to highlight the Fastplotlib API and show you some cool features. But before we get started, I just want to give a brief overview of the Fastplotlib API. So there's really three main components, the first being graphics, which are objects that are drawn, such as an image, line, scatter, or heat map, etc. These graphics get added to layouts, such as a plot or a grid plot. And then lastly, we have widgets, which are high-level widgets to make repetitive UIs easier to create. So for example, this would be something like an image widget, which allows you to really easily view and interact with in-dimensional image data. Also, just a note, we are running all these demos remotely on a workstation back on the East Coast in Chapel Hill. And here are some specs about the hardware, just to give you an idea of what we're running things on. But before we get into anything too complex, I just want to start with a very simple example, how you would draw a simple 2D image in Fastplotlib. So the first thing to do is to create a plot. And then once you have a plot instance, you can add a graphic to the plot. So in general, the way to add any graphic to a plot in Fastplotlib is to call plot.add, followed by the type of graphic that you would like to instantiate. So here we're going to add an image. And then to view your plot, you're just going to call plot.show. Just as a note, we're using Jupyter Sidecar here to render all of our plots on the side, but that's really just for convenience as we move through the notebooks. Definitely not a dependency for Fastplotlib. So once you have a plot rendered, you can very easily use the canvas to change the size, as well as we can pan and zoom our image as well. By default, the origin is in the bottom left-hand corner. So you can either manually change the camera Y scale, or you can simply use the toolbar to flip the image. And in general, the toolbar has a lot of useful tools. You can auto-scale the scene, auto-center the scene, as well as do something like toggle the maintain the aspect of the camera. And so if we just toggle this, that allows us to then therefore go and stretch and compress our image as well. You can also draw a polygon or record the plot. But really what's cool about Fastplotlib is that it has this non-blocking feature, and so graphics have what we call graphic features. So that would be something like the data, the colors, the color map, etc. And since Jupyter is non-blocking, we can dynamically change these graphic features after a plot has been created. So here we're going to, for example, change the color map. And then we also, on all of our graphic features, offer indexing, and this is what we mean by trying to have an expressive API that allows our users really fine-grained control over their visualizations. So for example, we could change all the x and y values, every 15th x and y value to 1. Or a little bit fancier, we could change every data value above 175 to 255. Additionally, we could edit the vmin, vmax, or we could reset that as well. And so that's just a simple introduction into how you would do something like plot an image in Fastplotlib. And next, I want to talk about how you would define something like an animation function in Fastplotlib. And an animation function is simply just a callback function that's going to get executed on every rendering cycle. So here what we're doing is we're adding some random data to a plot, and then on every rendering cycle, we're going to update the data of our random image to new random data. And so as you can imagine, that's going to give us something that looks like noise. But as you can imagine, maybe you have like really large image data, high dimensions, and you want to look at 2D cross-sections of your data. So I'm going to show you how you can do that first with Fastplotlib and SciPy widgets. And so we're going to look at the image.io cockatoo video from their standard library. And all we're going to do is add the first frame of the movie to the plot. And then we're going to have this callback function that links to the SciPy widget inslider. And so as we move through the movie with the inslider, you can see that the frames are getting updated. And now this is random access. So we're not playing the movie. This is updating the frame as we move through the movie. But so, as you can imagine, maybe using an update movie would be really tedious. And so we actually have this user-designed image widget that auto-generates a lot of these sliders to look through your dimensions for you. So here we're going to be looking at some zebrafish data, whole brain zebrafish data that's about 10 gigabytes. And so there's about 1,300 frames of 30 z-plane dimensions, and the frames are all 512 by 512 in size. And we're going to view each separate plane in a subplot. And so here we could simply just like put the movie on a loop and play. And so if we zoom into some of our subplots, you can see the individual neural activity over time. But just like before with the SciPy widgets inslider, this is also random access, so we could pause, and we could also have this. Also, a really neat feature of the image widget is that we can define something like window functions, which in this case, we're going to define a rolling average. And so, as you can imagine, with neural data, maybe we want to look at increased signal to noise ratio. And so we can use the mean here to do that. And you can see live how that changes the data. And so we're really interacting with our data and our visualizations after this has already been rendered. And so that is just kind of a brief introduction into Fastplotlib, as well as images, what you would do with them. And next, I just want to take a quick look at some more graphics that you could create in Fastplotlib. So first, let's take a look at some 2D line plots. So the first thing we're going to do is generate some data. And so we're just going to create a sine, cosine, and Ricker wave, and add all three of those lines to an individual plot. And so lines are graphics just like images, and so therefore they have graphic features that can be dynamically changed after a plot has been rendered. So here we're going to index into the colors and very simply change some of our cosine colors. And even more fancily, we can also directly set the red values of a given segment of the line directly from an array. But you can also capture changes to graphic features as events. And so here we're going to define a callback function and add it to the colors of the cosine graphic. And so every time that we change the colors, it's going to print our event data. And so here we're going to change every third index from 15 to 50 to cyan. And the event data is printed, but as you can imagine, maybe you would have a more complex callback function that you would have there instead, depending on what you're looking at. I also want to emphasize and highlight that you can have this same functionality with fancy indexing with color maps. So we're going to start with a simple sine wave that is just white. And for example, maybe we'll set the entire color map of this line to jet. But then we can also change the values of that CMAP as well. So we can directly set them to the y values of the sine wave, as well as the cosine wave. And then we can retain those values that we've set and simply just change the CMAP as well to something else. We can also set the values of our CMAP values qualitatively. So here we're going to create 4 sections and assign them to this cosine, the CMAP that we already have. And as well, we could retain those same CMAP values again and simply change to a new color map. Next, we're going to take a look at line collections. And so we're going to draw a 4x4 grid of circles. And we're going to set the CMAP qualitatively. And so essentially what you're going to see is these CMAP values here are going to be assigned. And so if you had something like classification or clustering and you had class labels or clustering labels, you could see how this could be really useful in labeling individual pieces of your data based on some categories. But while this might be a very easy intuitive example, I want to show you what that might look like in neural data. So here we're going to be looking at some calcium imaging data, and we're going to plot the identified neurons on top. And so here, random access again, we're just looking at the movie, and so we can just set that to play. And so basically what we have is a binary classifier of whether indices were identified as accepted or rejected. And so ones are going to be our accepted components, and zeros are going to be those that are rejected. And we can add those contours to our plot overlaid with our movie playing in the background, and we can see which ones are accepted versus rejected. And as you can imagine, that would be really helpful if you know, to look at specific contours and that were already identified as ones that perhaps are real neurons. But we can very easily look at other quantitative metrics as well. So for example, if we wanted to go back to looking to signal to noise ratio, we could just have a different kind of metric and just change our CMAP values as well as our CMAP. And so here what you're seeing is purple is going to be low signal to noise and yellow is going to be high. So maybe we would perhaps want to take a closer look at the yellow neurons as opposed to some of the other ones that have a lower signal to noise ratio. And so that's kind of a more applicable example of how this really fine-grained control of color maps can be super useful in analyzing and looking at your data. And so next, I want to show you guys kind of a performative example of how powerful Fastplotlib can be in plotting lots of data. So here, what we're going to do is generate some sine data that's like 3 million points across 1,000 sine waves, and it renders very quickly in Fastplotlib. And so as you can see, you can't even distinguish the waves at this point, but if we were to zoom in, we can start to see the lines. And you know, we can stretch, we can compress, we can easily zoom back out. And so, you know, maybe we want to change the color map of all of these lines, or maybe only half of the lines, or maybe we want to change every 5th index of half of our lines to white. And so, you know, we can zoom back in and really see that every 5th indice here is being changed to white. And so that's kind of a performant example of how powerful some of the plots that you can create with lots and lots of data. And so next I want to show a linear region selector, and what this is a linear region bounded graphic, which can move along the X or Y axis, and you can just define any callback function that you would like in what you would want to do with the selected indices or data that is bounded in this region. So for right now, we're just zooming into the data, and so we can select a wider range, a smaller range, and we can also move this along our data as well. And so lastly, I want to show you guys a heat map. So we're going to go back to looking at the neural data that we looked at before. So as you can see, we have the same neural data that we had before, some calcium imaging. And so as you can imagine, using a heat map when you have high time series data could be really useful. So here on the right, we have the temporal traces and activity over time of the neurons, and that can be linked to this heat map, and we can scroll through, and we could, you know, you could see very easily how a heat map might be a really useful graphic to have. And so next, I want to show you some more interactivity that is capable with Fastplotlib. And so we're going to continue looking at some neural data, And so we're going to see how we could register some click events to very easily further interact with our data. And so here we have the contours overlaid with our movie again, and so we can just set this to play. And then below we also have an individual trace. And so what we're going to do is use this high-level abstract function, part of Fastplotlib, and we're going to link the click event of the image graphic to the contours, and that's going to update the color, as well as update this graphic down here as well to show the corresponding selected neurons' temporal trace over time. So for example, perhaps we would maybe select this. And then, we can zoom in, and then, we'll stop the movie, and then we can play over time. And you could really, one-on-one evaluate components and see what their neural activity looks like, and if it's, correct, what has been identified, etc. And so that's just kind of a brief intro into some of the graphics, some of the interactivity that you can have with Fastplotlib. But originally Fastplotlib was designed with neural cases in mind, and that was a lot of what we showed aside from some intuitive examples. So we wanted to finish our demos actually with showing you some other data as well, because of the long-term goal of Fastplotlib is to really have a general purpose scientific plotting library. So here what we're going to do is just create a plot and add a movie to a plot. As before, we're back to using the IPyWidgets in slider, and so here we're just going to have a simple movie, horse, jumping over. And so we can use the polygon tool to draw a polygon, like so, around the rider and part of the horse. And so then what we're going to do is randomly sample 100 points from within our polygon, and we're going to add that as scatter. And so then what we're going to do is run a tracking model that's going to track these points over the course of the entire movie and run inference. And so here we're doing that there. And then we're just going to create a new plot that has the results of the inference as well. And we're just going to apply a general Gaussian filter to smooth some of the tracks. But as you can see, that now we have these tracking points over time. And so here we're tracking very simply using scatter to overlay this movie, and you see our points. But perhaps maybe the points aren't that helpful to look at. And so we could add a line collection to actually plot the tracks over time. And so here now we have some plots, and we have the tracks, and you can see how these tracks follow the scatter over time. But maybe even further, we would want to just quickly change the CMAP to color different things and take a look at some quantitative metrics. So for example, we could color earlier points versus later points. So here we've just set the color map of the tracks to show earlier points as purple and later points as yellow, and change the points of our scatter. And so you can see those points of the track in time according to when they occur. As well, perhaps maybe we would want to look at something like velocity. And so we'll take a look at the y velocity. And so here, red is going to be positive y velocity, white is going to be none, blue is negative. And so as you can see over the course of the video, these tracks really make sense to what the velocity is doing. And that was simply done by just changing the color map. As well, we could look at something like acceleration, the x or y component of acceleration. But really the whole point of showing you this was to show that Fastplotlib, everything is being done live, it's interactive, it allows for rapid prototyping and algorithm development without having to save movies offline and reload them. So you can very easily try different things or investigate whatever part of your data you would like. And so lastly, we just want to show you some more tracking data because we thought it was cool in a grid plot. And so we have already run the tracking on this, but we're just going to add them in real time. And so here what you're going to see is a 3x3 grid plot of some videos. And so we're still random access, scrolling through our movies, and then we're just going to add our tracks. And so these are colored the same way as before, with the time of being earlier to later, and you can see what those tracks look like. And so we just wanted to end by showing you, if you had lots and lots of data, that you are more incapable of looking at more data as needed. And so that concludes the demos, and I'm just going to turn it back over to Kushal to conclude our talk. Thank you.
Okay. Thanks, Caitlin, for those amazing demos. And I just want to stress that all those demos were done on a remote workstation, not locally. And it's just the Jupyter Remote Frame Buffer that is streaming basically a rasterized JPEG of an off-screen render locally to my laptop. So this slide actually got missed, sorry. I guess you already know all of this. I mean, I just want to stress, we've been working on this for only the past year. It's, just Caitlin and myself who've been working on this. And, we do have kind of, 2 key users who've been driving this development. Like Arjun is using this for live streaming of like medical biosensor data. And Eric Thompson, who is here, is using it for like large-scale neural imaging data. And we do have a roadmap that we want to try and get through by the end of the year. And we are running a sprint this weekend. So we're here until late Sunday afternoon if anyone's like either interested in trying to contribute, because it's in a very early stage, so it's it's pretty easy to get into, or if you're interested in using Fastplotlib for your use cases. And there are a couple of particular things that we would be interested in that are, which if anyone here is experienced with, would be great. And yeah, that's basically it. Any questions?
All right. Thank you. That was amazing. I can't wait to see it next year to see how much more progress you'll make in another year. That's amazing. Who has some questions? Because I have one. There's a question there. Okay.
It seems like a minor thing, but it's a major, major thing. What about text?
There is, text rendering is very new, and like in terms of pygfx, and like in terms of axes, that's also something that pygfx is planning to implement by the end of the year. So like, axes and text is something that, we're hoping to, start working on towards the end of the year and like refine early next year.
So if that comes along with the lower library of pygfx?
Yes, yeah.
Other questions? All right, so it was there was a lot of flickering going on. You busy idle. Is that the remote buffer thing, or?
Yeah, we are on Wi-Fi, and it is running remotely. So that's basically it. Like, if you're on a wired connection, you generally don't see that. It's the networking. Oh, and sometimes you might mean like the flickering, like with the image widget when you're zooming in.
No, sorry, I meant the busy idle state for the Jupyter kernel. Yeah.
Okay, yeah, you mean the circle thing.
Yeah.
That's just the communication with the frame buffer. I thought you meant like the flickering of the image, but yeah, that's not working.
Cool.
Yep.
Oh, there we go.
So you keep mentioning that you are doing the rendering on a remote machine. What can people expect with respect to rendering power with a normal, say, laptop machine with some non-expensive GPU?
Yeah, so like my laptop is about 6 years old, which probably has like the minimal requirements that you would kind of need in order to use something with Vulkan. The GPU is from 2017 or 2018, something like that. And it can do pretty much all of these demos except for the 3 million points with the line. I think we can do, I don't know if we can do 1 million with my laptop, but like, yeah, that gives you, I guess, an idea.
Hi, a great talk. I think Fastplotlib is super cool. I did have a question. I guess it's more from a maintainer standpoint. What's it like working with pygfx? Like, since it's so new and it's changing a lot, do you have to like work around lots of breaking changes? How much does that impact your maintenance experience?
Yeah, so the pygfx developers are really nice and awesome. So And I mean, I think their code is like pretty well written, so it's easy to, it's easy to dig into their code base and understand what's happening. But yeah, in terms of breaking changes, we've been, like whenever they do have breaking changes and major refactors, like, I think in like 1 or 2 months we've been able to implement them. But they are, I don't want to speak for, Elmar and Corin, but their goal is to have a stable API by the end of the year. And they've been like, I think they've been really pushing to try and meet that goal.
One more question?
So awesome stuff, super awesome. I'm curious about widgets. I'm guessing y'all support a lot of kind of little widgets like range sliders and things like this. Can you just talk about that and how easy it is to?
Everything that's shown is just callbacks from SciPy widgets. But if you're using a desktop app, if you're running it in a desktop application, you could use like Qt widgets. But one thing that we'd really like to have is like pygfx widgets, because then you could have the same widgets that are just rendered within the canvas, and it would be the same widgets regardless of what framework you're using.
All right, I have one more question because we're doing good on time. So you mentioned that this is all running in North Carolina. Is the Jupyter server also there in the kernel, or are those local?
That's what it
so
is.
Everything is over there.
Yeah, like you can see the URL, is not localhost.
Got it. Okay. Okay.
Yeah, exactly. It's just a Jupyter Lab instance that's running over there. Yeah.
Perfect. Yeah. Oh yeah. Making me run, Juan. I could talk to you guys while I run.
I want to tire you out for tomorrow morning so I can keep up. Hey guys.
Sorry. Also, the other thing is, so we are running our visualization on a 3090 on that workstation, but also the inference for those trajectories that we showed in the end is running actually on the same GPU. So it's, just to give an idea of what is the requirements of this. Yeah. Sorry. Go on.
Yeah. This actually is a minor thing, but in terms of the coordinate systems, like, are you gonna flip them so that the images come the right way up from?
Yeah. So I think pygfx has been working on standardizing their reference system, and I think they just kind of finished that. So we've been thinking about like what is a nice way to do it that works for if you want to draw images or if you want to draw time series data or combine them. And that's just going to be us trying to decide how to expose that nicely and make it work for all different use cases.
Yeah, I think you have a harder job than Napari because we're very image centric, so top left makes sense. But if you want to do the same, like this is the whole problem we have with map.lib is like they're different coordinate axis conventions.
Yeah.
Anyway, good luck.
All right, still 2 minutes left. Any other questions? Hearing none and seeing nothing in Slack, let's thank our speakers.
Thanks.